Hey, our first speaker of the morning session is Vasily Pestun, and he will talk on multiplicative Higgs bundles.
Thank you very much for our invitation. It's a pleasure to be here in Uppsala and speak to this audience. So my project is done in collaboration with Christopher Elliott. He's a postdoc in HS. He moves to UMass Amherst, and the paper is this one, Multiplicative Hitchens Systems and Supersymmetric Gauge Theory. Let me start. So first, I will recall what is a Hitchens system. Most of you know, but still, you consider a curve and a system of Higgs bundles. On a curve is defined as follows. You consider a pair of a principal G bundle, where G is a, let's say, complex reductive group, and a section phi of the following Lang bundle. That's it takes value in the adjoint representation. That is Lie algebra valued, and also with respect to their space-time indices, it transforms as a holomorphic one form. That's a section of the canonical bundle. And we can allow poles at a divisor, so that's denoted like that. So then there is a theorem due to many people, starting from seminal work of Hitchin, and then Markman, Batashin, Mukai, Turin, and others, that there is an algebraic integrable system on the modular space of these meromorphic Higgs bundles. So this Hitchens system plays a prominent role in the modern studies of mathematical physics and string theory. Several points are the appearance of it in geometric Lagrange program by Belenson-Drinfeld, and then Kapustin-Witten relation to maximal supersymmetric Young-Mills. Then it's a construction of the compactification of the six-dimensional 2,0 theory on M5 branes to down to the 4 dimensions, to n equals 2. That's a Gayota construction. And the Seiberg-Witten integrable system for this n equals 2 theory comes as an integrable system of Hitchin defined by that choice of the curve of algebraic curve and the bundle on it. After quantization, that Hitchin system relates to the Nekrasov functions of the corresponding 4D theory, the so-called Nekrasov-Shetashvili limit. And after hyperkähler rotation, when you treat the system not in complex like structure I, but in a rotated one, in twist rotation, that relates to the Toda theory and correlation functions of W algebra, this famous Aldai-Gayota-Tajikava relation. Now, let's see how the story is generalized. So, in fact, the principal construction was done by Danagi and Geitzgary, and they proceed as follows. So, they defined so-called abstract Higgs bundle on X, and an abstract Higgs bundles is a pair P comma C, where P is a principal G bundle on X, and C is a sub-bundle of the adjoint bundle of P. So such that each fiber of C consists of a centralizer in G of a regular element. Then there is an equivalence between an abstract G bundle and abstract spectral data. That's an abstract version of the spectral curve for a Hitchens system, where the abstract chimeral cover comes with a suitably transformed T bundle on X tilde. So that's construction of Danagi-Geitzgary. And the point of it is that the usual Hitchens system can be viewed as an example of this abstract construction when you take the abstract bundle P comma C and consider it valued in the canonical bundle K of X by adding a section phi, that's the Higgs field, the usual Higgs field of the Hitchens system, and to the spectral data, and you add W invariant collection of maps from X tilde, from the abstract spectral cover, to the cotangent bundle on X. So, taking this construction, we can consider different values, not necessarily a line bundle Kx. We can replace that line bundle by a family, let's say Y, of groups fibered over X. And then a Higgs field phi could be taken a section of C tensor Y. Then similarly, the spectral data can be deformed and modified like that by collection of maps X tilde to Y. And in this way, you get a modular space that we can denote Higgs bundles, G Higgs bundles of Y over X, where Y is not now T star of X, but more generally could be taken with more general group values. So now suppose that Y is fibered over X and the generic fiber is an elliptic curve. Okay, then Danagi has shown that the modular space band G on Y, so that's the modular space of principal holomorphic G bundles on Y, is isomorphic with the modular space of G Higgs bundles on X with values in this fibration, where each fiber is elliptic curve. So if Y itself is a two-dimensional, algebraically integrable system fibered over X, so then the resulting band G of Y, that's Higgs of G of Y over X, is an algebraic integrable system. That's the result of Danagi. Now, let's consider three options that we can naively take in the vertical direction of this one-dimensional abelian group. So there are three cases. Naturally, you start from a complex plane, and you can consider just complex plane, or you factor it by Z, or you factor it by rank 2 lattice and get elliptic curve. So the elliptic curve, the multiplicative group, that's C star or C mod Z or GM, and the additive group. So the case of the usual Hitchin system, so in this notations corresponds to the additive case when the fiber over X is C, just a line, or the group under the addition. And in this case, the Higgs G of Y over X is the usual Hitchin system. The opposite case, when the fiber is elliptic curve, then this is the space of the bundles, of the G bundles on the two-dimensional elliptically fibered surface Y. And then there is intermediate case. And in the lectures of Ron Danagi in 2003, there is a question which is posed, so that the modular space corresponding to the additive case is the Hitchin system, the modular space corresponding to the elliptic case is elliptic vibration, and the question is there an interesting geometric interpretation of the remaining trigonometric case where the values are taken in the multiplicative group? So this talk will be about this remaining case, about multiplicative group, and so the name is multiplicative Higgs bundles. So that's what I just announced. That's the purpose of this talk. And now let me first outline the results. So I will state as a bunch of theorems. So theorem 1, we consider the modular space of these multiplicative Higgs bundles with the following data. You pick, I will explain later what the data is, but you pick a divisor D on X and define a behavior of the Higgs field around this divisor by choice of co-weights of the gauge group. And then it turns out that the recital modular space, also when you fix a framing at infinity and the value of the Higgs field that's a framing at infinity, it turns out that this space is a finite dimensional algebraic variety, and you can compute its dimension. Its dimension is given by the pairing between the sum over all co-weights and the Weil vector rho. The point is that this symplectic algebraic variety is in fact a symplectic leaf in the infinite dimensional Poisson-Lie rational loop group. So what's this group? It's a group of the rational functions on X valued in reductive group G, such that at the infinity the value is 1, that this is the subscript carries this information. So that rational loop group carries a natural Poisson structure of Sklenin type, which is induced by the rational R matrix. I will explain later. And so in this way, the symplectic structure on this modular space of multiplicative Higgs bundles is canonically induced by the Sklenin R matrix or Sklenin Poisson structure. So the next point is that there is integrable system fibration from the multiplicative Higgs bundles in parallel to the story of the additive Hitchin system. So the fibration over a certain base and the projection, that's the Hamiltonian functions, if we say, are given by the adjoint invariant functions evaluated on the Higgs fields. That's, we can, for example, pick a characters of the group. So next point is that if we assume some conditions on G and framing like semi-simple condition. Then there is a symplectic reduction of the multiplicative Higgs bundles of this symplectic variety by the action of the maximal torus, the gauge group. So we denote it like that. T is the maximal torus. And the Hamiltonian functions for the action of this maximal torus are generated by the residues of the Hamiltonian functions at infinity. So the dimension of the reduced space is naturally obtained by subtracting twice of rank of the G. And the reduced space carries a structure of vibration of algebraic integrable system where Lagrangian fibers are now generically compact abelian varieties outside of discriminant locus. They are nice compact abelian varieties, and consequently you can define a prepotential for the system that's cyber-Newton prepotential in the context of the gauge theories when we have a correspondence to that. So moreover, holomorphic complex structure on this reduced space can be lifted to a canonical semi-flat hyperkähler structure. So there is a natural hyperkähler metric on the space. And now we come to another side of the story, to the monopole story. So before I was like in the realm of the algebraic geometry, and now we come to, let's say, partial differential equations. So you consider the modular space of solutions to singular monopoles, so-called Dirac monopoles or monopoles with Dirac singularities, on a three-dimensional space, which is taken x times a circle, and you lift the positions of the singularities for the Higgs field to positions of the singularities for the monopole fields in the three-dimensional space. And there is a map from the locus of the polystable Higgs bundles to the monopole solutions. So, and the hyperkähler modular space of singular monopoles, of these periodic monopoles, viewed in the twistor structure zeta. So twistor structure is the choice of the direction in the three-dimensional space by which you align the complex structure picture. So zeta equals 0, it corresponds to the vertical direction. So in this complex structure zeta equals 0, the modular space of singular monopoles is viewed as a holomorphic symplectic variety, and it's isomorphic with the symplectic structure to the symplectic leaf in the Sklenin-Poisson Lie group G1. So if you came from the question, what is the symplectic structure in the modular space of monopoles, like you want to quantize a Coulomb branch or something, here's the answer. You take the Sklenin Poisson structure on the Lie group, you pick their symplectic leaf, and their reduction or restriction to that symplectic leaf is this holomorphic symplectic structure on a modular space of monopoles. So that explains how Yangian comes after quantization. So next point is that we can consider now twistor rotation and ask what's the geometry, what's interpretation of this geometry after the twistor rotation. So recall that in the additive case, in the case of Hitchin modular space, after twistor rotation, if you look at its holomorphic symplectic variety, you find that it's equivalent, isomorphic to the modular space of complex flat connections. That's a space of pairs PA, where P is a holomorphic G bundle on X, and A is a holomorphic 1-0 connection 1 form. So a parallel statement for multiplicative Higgs bundles is the following. So we take the limit R to infinity, the radius of the circle to infinity, with this constraint between the twistor parameter and epsilon. This limit was also considered in a work by Gayotta, sometimes called Gayotta limit. The modular space of singular monopoles on X times S1 at twistor point zeta is isomorphic as holomorphic symplectic variety to the modular space of G epsilon connections on X. So what are epsilon connections? Epsilon connections are difference connections, contrary to the usual differential connections. And epsilon connections, by the definition of it, it's a morphism between a bundle P and a pullback of that bundle P by epsilon automorphism of the base curve. So for example, if epsilon is a group which shifts on X point to X plus epsilon, plus epsilon, plus epsilon, plus epsilon, and so on, then the epsilon connection, its trivialization amounts to solving the difference equation, where psi, a section of X plus epsilon, is given by multiplication of the connection. It's a group value thing, contrary to the Lie algebra value thing of the usual connection, to psi. So we are talking about difference equations like that. In this theorem, X, you can take it compact. It's necessary that X is flat, so it could be compact like elliptic curve, or we'll consider, as I'm showing on this slide, a non-compact case when X is C, or compactification to P1. So that we'll call the rational case. We'll take X to be C, and then the notations are that we choose dx, that's just trivializing one form on the C, dx, the natural one form, which has degree 2 pole at infinity of the compactification on P1, and the divisor D denotes a divisor which is decorated by a choice of a co-weight at each divisor point. So it's weighted in the dominant co-weight of the co-weight lattice. And the co-weights at each point are denoted by omega I check. Okay, so let's proceed to the definition. It's from Hartubis and Markman, work 2002. A multiplicative of G Higgs bundles framed at x infinity, that's point at infinity, with singularities at D, is a pair PG, where P is a principal bundle with framing fixed at infinity, and G is a section of the group valued adjoint bundle, such that near each singularity there exist local holomorphic sections, GL, GR, such that the Higgs field G is given by this singular part, x minus xi to the omega I check, modified by some non-singular multiplications from the left and to the right. And we think about omega I check as a morphism from C star to the maximal torus of G. So the element at infinity, this G infinity, is called framing, and the theory is more or less independent on the choice of this framing. We'll just assume that it's regular semi-simple. Now, this is more abstract presentation for mathematicians. So in a formal neighborhood of each puncture, a restriction of the multiplicative Higgs field defines an element of algebraic loop group, that's G double bracket Z, where Z is the difference between x and xi, and this element is well defined up to the positive part of the group, G square bracket Z, and the singularity class, it doesn't change under the left or right multiplication by G square bracket Z. So consequently, the singularity class is a coset in the affine Grassmannian, where you take G double bracket Z and quotient by the square brackets from the left to the right. That's Grassmannian. That's an orbit of Grassmannian under the positive part of the loop group. And orbits in affine Grassmannian are known to mathematicians to be in canonical bijection with dominant co-weights of G. So a choice of such orbit is like a fixing of the degree at each puncture xi. Okay, so the modular space, then we'll study the modular space. The modular space of such pairs with a framing at infinity, a choice of singularities at divisor, and a choice of x. And that's what we denote by M Higgs framed G of xd. These spaces, they have been considered before, sometimes under the names of modular space of G pairs. Earlier works in these directions are by Batachin, Artyunov, Frolov, Medvedev, Cherkis, Kapustin, Braden, Chernikov, Dolgushev, Levin, Alshanetsky, Zotov, Hurtubis, Markman, Frenkel and Go, and Boutier, and there are possibly others I mentioned which I found. So for us to proceed, we want a Calabi-Yau condition on X. So while the structure of this multiplicative Higgs bundles, it makes sense for any X, there is a canonical symplectic structure on the space, which is interesting for us for the quantization, etc., only when the curve X is a Calabi-Yau with a specified, with a choice of a section of the canonical bundle Kx. So that the section, if we think about X as a quotient of C by lattice of rank 0, 1, or 2, it's just dx, the one form dx. And for the rest of the talk, we'll focus on the horizontally rational case when x is C, or compactification of C by one point at infinity, P1, equipped with one form dx, so it has degree 2 pole at x infinity. While the case of when x is elliptic curve, it was studied in Hurtubise-Markman. Okay, now let me say more clearly what's rational Poisson Lie group. So K of x denotes field of rational functions on x, and G of kx is the infinite dimensional Lie group, which is valued in this field. And G1 of kx denotes a subgroup of elements which are framed at infinity. That's G of x infinity equals to 1. So then it's a classical work coming from mathematicians working on classical integrable systems, Sklyanin, Reshetikhin, Rayman, Simonov, Tinshansky from 80s, that this loop group, it carries a structure of Poisson Lie group. So first of all, it's a Lie group, and second, there is a Poisson structure in it, and that Poisson structure is compatible with multiplication. That's if you multiply two elements of the group and push the Poisson structure by this multiplication, it coincides with the Poisson structure on the target. And the definition of this Poisson structure, I mean, the formula definition comes with a rational matrix of this form, where omega is a quadratic Casimir and G tensor G induced from a killing form on G. Okay, 48. Now let's proceed to write a formula for a Sklyanin bracket to present a concrete formula for the symplectic structure later on the modular space of Higgs bundles. So given any algebraic function phi on a group G, complex valued function, and the point x on a base curve, we consider evaluation functions phi sub x. So that's evaluation function you just take a value of the Higgs field at point x and plug in into the function from G to C. So you get the value of the function at point x. And let's write down the formula for the Poisson bracket on such evaluation functions, phi x1, phi x2. So first of all, let's introduce the left and right gradients of evaluation functions by the derivative of the left and right multiplication. So if xi is a vector field, then you take action by the xi from the left on G, and the differential would be the left gradient. Or if you take the action by the right multiplication of exponent of xi to G, and the differential would be the right gradient. So this is the standard notations for the left and right gradients. And then the Poisson bracket of two evaluation functions, phi x1 and psi x2, G is given by this Sklyanin formula. So 1 over the difference between 2 points x1, x2 comes from the denominator in the rational R matrix, and the rest is essentially canonical lift of the Poisson structure from the Lie bialgebra to the Poisson Lie group. So it's a pairing between the left gradients minus the pairing between the right gradients. And the pairing is the pairing on G star induced from a killing form. Now, with respect to this Poisson structure, first of all, let's look how adjoint invariant functions behave. So suppose that phi is a adjoint invariant function, and if it's a adjoint invariant function, then the left gradient and right gradient are the same because of adjoint invariance. And consequently, if we pick both adjoint invariant functions, then their Poisson bracket is 0. So they are commute. They conserved in parallel. So they can be used to build a system of commuting Hamiltonians. And consequently, more abstractly speaking, the image, the intersection of the image of inclusion of M Higgs in the formal loop group G1 of x minus 1 with the fiber of the Chevalier map, you take the adjoint invariant functions, so the target could be viewed as a maximal torus mod Weil group. So this image is isotropic for this Sklyanin Poisson structure. That means that essentially that these two functions, they Poisson commute. Okay, so now we'll proceed to demonstrate the core steps in the proof of the theorem which was outlined. So this is the theorem, but we want to show that if you take Scaling-Poisson structure on the loop group and consider this symplectically, first of all, that's a multiplicative Higgs bundle, and secondly, we'll compute the Poisson the symplectic structure there from the rational R matrix. So first, consider the deformation complex and identify the tangent space to multiplicative G-Higgs pair PG at some point. So how would we do the deformation? Well, so a deformation or in the tangent space at the point of group can be identified with the tangent space at the unity by the translation by the right or left multiplication. So in the naive matrix notation, like you choose a faithful representation, you can present the deformation as follows. You multiply by the Lie algebra element psi L from the left to G, or you multiply it from the right. And there is, of course, an equivalence relation if you move G from right of XL to the left of it, then the deformation by choice of such pair, where psi left and psi R are shifted by these elements, is equivalent to deformation by such pair. So deformation complex can be built from taking pairs of G-valued sections, psi L, psi R, by quotient by the equivalence relation of this form. So we can write it as taking this direct sum of GP adjoint Lie algebra valued bundle with itself and quotient by the action of GP. So then there is the usual gauge transformation, so a change of automorphism frame, and consequently the deformation complex of multiplicative G-Higgs pairs on X can be identified with this, where A denotes a quotient written on the previous page, this one. So this is A. And here, the shifted Lie algebra valued bundle denotes the infinitesimal gauge transformation, so automorphism of the gauge bundle. Now, if you go to the rational case with the framing fixed at infinity, like you pick a trivial G bundle on P1, there are then no non-trivial automorphism of it because we fixed the framing at infinity and because there are no non-trivial holomorphic functions, right? So in this case, all deformations, they sit in here, just in this term, and we forget about this term. So now let's compute the tangent. Let's consider this tangent space and compute its dimension, for example, like to touch it. So so this is the equivalence relation, and if we can check, for example, we can change the right section to 0 by adding corresponding shift to the left section. So any pair psi L, psi R is equivalent to the pair psi L plus adjoint G action on psi R, comma 0. So now let's assume that G of X is generic near each singularity. That's it's regular semi-simple as X goes to singularity Xi. And in this case, this map adjoint of G of X is diagonalizable near Xi. So then define H sub X to be centralizer of G of X and assume that there is a limit H sub Xi when you move X to the point Xi. So then take the usual Borel type splitting of G into the Cartan algebra and plus the sum over root spaces G alpha X, and let E alpha sub X be generator of each root space. So then we can present very explicit formula for the deformation of the multiplicative Higgs fields. That's a tangent space at some point G of X, and it would be generated by the sections of the following form. So you take a generator in each positive direction with respect to a co-weight singularity given at this point. So omega I check I is the co-weight. This is, we consider a root which has a positive pairing there. And we allow singularity in the direction of the root space E alpha, which is positive with respect to I, of arbitrary power up to up to this one. So why? Well, because by the change of equivalence frame, such a section can be moved to psi L and psi R picture where both psi L and psi R are holomorphic. So it means that this deformation doesn't change the singularity type. So it's similar to decomposition of a rational function by a sum of its poles. So in this case, the poles at each singularity xi are given in the direction of the positive root spaces with respect to the decomposition or by positive and negative root spaces of g of x. So consequently, the dimension of the tangent space is just given by the number of coefficients here. So you sum over all singularities over all co-weights, and you sum over all positive roots. And when you do that, you have some. You express it in terms of the Weil covector, which is 1/2 of a sum over positive roots. So that's a formula which appears often in these studies. Now, okay, so now we identify this algebraic variety is tangent space, and we want to show that it's in symplectic leaf to a Poisson structure on the loop group G1 of Kx. So what would it mean? So pointwise, a tangent space is in a Poisson variety M is defined to be the image of the Poisson structure map. That's a map from the cotangent bundle of M to tangent bundle of M. And then Jacob identity will guarantee that distribution of these subvarieties is integrable, so it will define the symplectic leaf. Now, to a local function called Hamiltonian phi from a Poisson space to C, in neighborhood of a point, we can associate a Hamiltonian vector field xi sub phi as pi times differential of phi. And then the Hamiltonian vector fields xi phi, xi psi for arbitrary phi psi, they will belong to a tangent space of a symplectic leaf. So what would be a symplectic structure which is compatible to Poisson structure on symplectic leaf? It's just this one. So if you plug in these vector fields associated to Hamiltonian functions psi and phi, so that's psi of x, this x is xi, psi of xi, psi phi is equal to pi evaluated on the differentials of functions phi and psi. Okay, so we'll start from symplectic, from Sklenin bracket and Poisson structure on the loop group, and we'll show 2 points. We'll first show that the image of pi of the Poisson structure belongs to the tangent space to the multiplicative Higgs bundles. And second, we'll determine the symplectic form such that if we evaluate the symplectic form on the vector fields, on the Hamiltonian vector fields, it coincides with the evaluation of Poisson structure on the differential of these vector fields. So now we'll go to very concrete formulas. So let's start from, let me explain the explicit formula for the symplectic structure on this multiplicative Higgs space. So let Ui be small disks around punctures xi and represent the tangent vector field to the Higgs space, to the multiplicative Higgs space by a set of sections of these pairs, xi L, xi R, subscript I, regular in each disk Ui. And the rest away from those small disks by subscript 0. So then this is the formula. The symplectic structure on such two variations on such two vector fields, xi and xi prime, is given by the sum of the following residues. You take contour integral or you take residues in each point xi of the pairing between xi I and xi 0 left and xi I R and xi 0 prime right. So first, let me demonstrate that this formula is in fact well defined. Remember that xi L and xi R are pairs considered under equivalence. So we want to show that if we make this change of the equivalence frame, we'll start from the change in the second argument by this deformation, then omega remains invariant. So it's actually a formula which makes sense on the quotient. So if you add this deformation to psi 0 L prime, then omega shifts by this deformation, and we can compute it. And you see here that the deformation, in fact, goes to 0 because using the equivalence, one can transform the variations in i's frames to the variations in the zeros frame away from the disks, and by deformation of the contour integral, the contour integral comes to be equal to 0. So omega is invariant under the equivalence in the second argument. Then we can also explicitly demonstrate that omega is antisymmetric. You do in two ways. You either use equivalence in the second argument to bring it to the psi 0 L and set psi 0 R prime to 0, and then the formula evaluates to this form where you take a residue pairings between psi L over each puncture I and psi I R prime over each puncture I with adjoint map. Or alternatively, by equivalence frame, you can set psi 0 L prime to 0, and in this frame, the formula becomes equal to this expression where you pair right value with adjoint inverse adjoint transformation of the left section. So, and by comparing these two expressions, you see that omega is antisymmetric. Okay, so it's antisymmetric. It's invariant under the change of equivalence frame in the second argument. So then it's invariant also under the first argument, and so it makes sense as an antisymmetric form on the quotient. So now we'll demonstrate that this symplectic form, well, so for antisymmetric form, it actually comes from this Klein-Poisson structure. So we want to make a computation. We'll take two evaluation functions, consider first Poisson bracket for them on the right, and compare with evaluation of the symplectic form on the corresponding vector fields. So we'll choose these equivalence frames for their vector fields in the charts i's given by this formula, and in the chart 0 given by this formula. Well, maybe the slides will be quick, but all details in the paper. So who is interested can check the computation there. And now we evaluate the symplectic form from the definition. It boils down to a contour integral and taking the residues. And when you do the computation, you find that indeed that symplectic structure evaluated on the corresponding Hamiltonian vector fields matches the Poisson bracket between those vector fields given by the Klein R matrix. So that's the main point. Now let me come to the switch context and come to the modular space of periodic monopoles. So we'll consider this nonlinear partial differential equations, which are reductions of self-dual equations from 4 dimensions to 3 dimensions, sometimes called Bogomolny equations. Concretely, we'll take X to be R2 with a flat metric, and M to be a flat 3D Euclidean manifold, which is product of X and S1. We lift the divisor to the 3-dimensional space of punctures on M, and let GC be denote the compact real group associated to the complex reductive group G. PC will be a principal GC bundle on 3D space equipped with a smooth connection A, and G-valued scalar field. That's the Higgs field in 3 dimensions. It's Lie algebra valued, contrary to the G of X, which was group valued in the previous slides. So this is reduction of the fourth dimensional component of the connections if you do the monopole equations by reduction from the 4 dimensions. So then the monopole on M with Dirac singularities is a pair of A phi which satisfies these self-dual equations in the 3 dimensions, right? And the definition of the singularity for the monopole near each point is simply that you choose a coweight and take the image under this coweight of the unit U1 Dirac monopole with a singularity at M. And unit U1 Dirac monopole is this famous configuration which has a unit flux magnetic flux around the two-sphere, which links to the point of singularity. Now, from given the monopole on x times S1, we can restrict the fields A phi to a horizontal slice by choice of any point on S1, let's say the point S0, which doesn't contain any Dirac singularities. And then by just looking on the 0,1 part of the horizontal connection Dalbo bar, we find the structure of holomorphic G bundle on X. And then monopole equations will apply like in the Hitchin paper that this combination is holomorphically annihilates by del bar. So, which in turn implies that in the trivialization, if you pick trivialization where del bar of its connection A is del bar, then the holonomy of the connection in the vertical direction of AS plus phi is holomorphic. So hence, therefore, we have a holonomy morphism from the monopoles to M Higgs, and that's essentially a construction of Kapustin and Cherkis paper. So then there are some technicalities. We'd like to consider a subset of this space of G Higgs bundles called polystable bundles, and essentially the definition of this polystable subset are those which are in the image of the reverse map from the monopole spaces to the Higgs bundles. So it's in the spirit of Donaldson, Uhlenbeck, Yao, or Kobayashi Hitchin correspondence. So let me go quickly here. There is you can run like a heat equation on a holomorphic G bundle on a complex surface. That's a paper of Donaldson, and find a harmonic metric which satisfies Hermitian-Yang-Mills equation. So that would be correspondence between algebraic geometry and differential geometry. There is a similar construction here. It went from the paper of Donaldson to Simpson, and then, excuse me, to Simpson, and then Mochizuki, Charbonnet-Hortobis, and following Mochizuki, a very recent paper, he relaxed one of key assumptions in the Simpson paper and was able to show that this correspondence holds on a non-compact space C2 times S1. Okay, so then the space of singular monopoles, it comes with a natural hypercolor structure, like all we know, and so there is a twistor zeta family of holomorphic symplectic forms. Then we consider this correspondence also in zeta-rotated complex structure. I will accelerate here, and maybe just make, maybe I will finish with this computation. One of the key computations is that if you consider the symplectic form on the monopole modular space evaluated, let's say, in complex ratchet zeta equals 0, then we want to show that this symplectic structure in the modular space of monopoles is isomorphic to that symplectic structure on symplectic leaf in Poisson-Lie group, for which I've given you a formula previously. So let's take a monopole. Let's consider this holonomy of the connection around the vertical circle. And now let's consider a deformation of the monopole connection. And since we have the Bogomolny equations, which can be written in the four-dimensional notations as 0,2 part of the curvature equals 0, it follows that deformation of a connection, there exists a potential, B scalar valued potential, such that deformation of 0,1 part of the connections is del bar of this potential. So then we want to evaluate the symplectic form on the monopole modular space, canonically defined by this formula, where V is the Calabi-Yau structure on the complex surface. And here we have this deformation in terms of del bar of B and del bar of B prime. Well, the trick is just to integrate twice using the Stokes formula. So it's on this slide. First, you integrate by the Stokes to the boundary of the UI disks, and the value would be B del bar Bi, and then you will integrate once again using the relation between the different frames here. And after this computation, you will find that the symplectic form in the modular space of monopoles is given by this formula, which you have seen before. Namely, it's a pairing between psi left and psi L prime variations between 0 and ice frame, and with the difference of the right relations. So this exactly matches the formula I've shown you before, derived from this Kleinian structure. And so this proves that the symplectic structure defined on monopoles coincides with the one defined by the rational R matrix. So that's a summary of that part, and closely connected works would be Gerasimov, Kharchov, Lebedev, Ablezin on Yangian and quantized singular monopoles on R3, and then Kamnitzer, Webster, Wicks, Jacobi on Yangian and slices in affine Grassmannian, and Braverman, Finkelberg, Nakajim on Coulomb branches and slices in affine Grassmannian. So this slices in affine Grassmannian is a particular version of those module spaces when all singularities are concentrated at 0. So you can view this work as deformations of this slices in affine Grassmannian. Okay, I think how much minutes I left to? Like 5 or 3? Yeah. Yeah, okay, maybe in 2 minutes. Okay, so I will compact that. Okay, so epsilon twist. So like in Hitchens' paper, we can study the modular space of Higgs bundles since it's hyperkähler variety in various complex structures. And in particular, here we'll do similar idea, but in the multiplicative case, you consider twisted product of x times S1 over epsilon, which means that if you move the curve x with an automorphism epsilon over S1 and glue the images between 0 and 2 pi with the shift by epsilon. So then the resulting modular space of monopoles, it also carries hyperkähler metric used from the flat Euclidean structure here. And consequently, one can show that the space is isomorphic to the space of these epsilon difference connections, right? Which replaces the modular space of flat connections in the additive case of Hitchens system. So finally, I will mention a point about Steinberg section. It's essentially a talk that I gave in 2017 in string mass. An analog to a constant section or Hitchens section in the additive case of Higgs bundles. In the multiplicative case, there is the so-called Steinberg section, which goes in backwards from this Chevalier projection to the maximum torus quotient by W, or from the group valued adjoint invariant functions back to a choice over an element of G. So this is constructed by Steinberg in 1965. And you can essentially generalize that construction for the affine loop group. And what comes after the epsilon twist is so-called space of Q operas. So that's the final points that I want to show, how it connects to the other research. So first of all, that's this brane of operas. It appears as a mirror of the canonical coisotropic brane in the classical work for the additive Hitchens systems. And here, the expectation that it also quantizes the expectation that it plays a similar role in the multiplicative case. So concretely, if you do quasi-diagonalization of this epsilon different operas, you find the beta ansatz equations for the spectrum of the quantized integrable system. It's in these papers. Or if you do another quantization, like if you first consider epsilon difference operas and then quantize them in that rotated symplectic, holomorphic symplectic structure, then you'll find this epsilon comma h bar in this notation. So Q1 comma Q2 W algebra whose currents known as Q1 Q2 characters. And to conclude, that's also connections to other works. So that's I mentioned this modular space of multiplicative G bundles. It comes as Coulomb branches of AD queer gauge theories studied in these papers. SYZ duality on the fibers It's like a geometric picture for the algebraic presentation of Q-geometric long lengths, Frenkel-Reshetikhin and Ganagic Frenkel-Okunkov. This I mentioned. And so Q1, Q2W algebras, that relates to the vertex algebra at the corner, Gayot-Rabchak, and the Kocha of Kontsevich-Stoibelman. And final point, quantization of this modular space of multiplicative Higgs bundles by the path integral, by the usual path integral of physicists of the form PDQ, that's the inverse of d of omega, it leads to a semi-holomorphic Chern-Simons theory when you extend the three-dimensional space by additional line. The idea is in Nekrasov's thesis 96 and Costello, Witten, Yamazaki work gives the detail, and it's like morally speaking, it's parallel to the quantization of the flat connections, how the quantization of the flat connections on a Riemann surface X led to Chern-Simons theory on the three-dimensional space X tier 1 in the Witten's paper. So here you replace like one Durham direction by Dalbo direction, so the bar and T. It gives this semi-holomorphic Chern-Simons theory, which quantizes the modular space of Bogomolny equations. Okay, thank you very much. I stop here.
Are there any questions?
So at the beginning, you said our regular semi-simple framing at G infinity. Yeah, is it related to the CP2 case for Donaldson, that framing at line at infinity for ADHM or things like that? But I didn't understand.
Well, this choice of regular semi-simple framing at infinity ensures that the resulting modular space is polystable, namely that there is a corresponding harmonic metric and the corresponding solution for the monopole equations for the compact group. So it's like in the it's like polystability equation restricted to the behavior at the infinity.
Are there further questions? Okay, well then let's thank Vasily again.